So we have had discussions on coating by physical methods, by diffusion control methods from the solid state or the vapor state. We also discussed a large number of techniques based on aqueous or molten bath, including electrochemical deposition techniques. You also heard various approaches of spray-based techniques, which are plasma or plasma-based techniques, for example. We are now going to discuss this is going to be the 45th lecture, and we are going to discuss the physical vapor deposition as one of the possible methods of producing coatings. But for a difference, these coatings are going to be thin, fairly thin coatings, usually in the tens of microns range. I mean, in special cases, one can go up to millimeter, but usually they are just a few micrometer thick coatings. So that's why these coatings are typically called thin films, rather not even coatings. So as the name suggests, physical vapor deposition, the process requires only a change of state, physical state. So you can deposit a thin film of elemental metal or compound on any kind of engineering solids for a small area or a larger area. The process is based on thermal evaporation. So essentially, you take the material to be deposited and evaporate it by way of heating, usually resistance heating. You do this primarily to improve the hardness or all the most important tribological properties, starting from friction to wear and erosion and other processes. There could also be utilities based on improvement of functional properties, which can be anything from conductivity to reflectivity to so make it amenable to various kinds of other functional applications. Similarly, this also can impart resistance to corrosion, resistance to tarnishing at room temperature, degradation, or even against oxidation. The difference, as is mentioned already, is in the fact that we are dealing with fairly thin films. So obviously, we need materials in order to take to the vapor state. We need materials with very high vapor pressure so that they can, by heating, we can easily take them into the vapor state, and they can create a saturated vapor pressure around the material or component to be coated. So first we take the material that we want to coat and the component that we want to coat both inside an enclosed chamber, and then evacuate and create fairly high vacuum, over 10 raised to minus 5 millibar or even higher vacuum. We may have arrangements for heating, may not have arrangements for heating. Heating separately, I mean ancillary heating processes for the substrate. We should also have a controlled atmosphere. We may create a controlled atmosphere, which could be simply rarefied chamber, high vacuum, or inert gas like argon, or we can even have a reactive gas in some very special cases. But remember, the evaporation is done by heating, but this heating here refers to the possibility of heating the substrate, which actually you are getting coated. So you can coat pure metals like gold, titanium, silver, in special cases maybe chromium or nickel, or materials which actually, but generally you choose metals which actually have fairly high vapor pressure. So they can be coated or deposited, and this actually also is a standard synthesis or processing technique for creating wear resistant coating or low friction coating on machine tool, for machine tool manufacturing, for semiconductor industry, creating various IC integrated circuits or various other kinds of components. In jewelry and ornament industry, this is very popular. It can be also very, very useful for precision instruments to create a matching coating to match the coefficient of thermal expansion or friction coefficient and so on. Similarly, also is useful in metalware industries. Typical thickness we are talking about is only 2 to 5 to 6 micrometer. not even 10 micrometer, whereas in case of CVD, one can go the chemical vapor deposition, which we'll discuss after a couple of lectures. You can create slightly thicker coating. So here what we actually have to understand is that this is coming from the vapor state, and if you build on a very thick coating, the stresses at the interface is going to be fairly large, which is going to be harmful. So we prefer to create a very thin coating. But we need to clean the surface well, remove not only the any kind of oil or grease, but also any presence of thin oxide layer, because that's going to then not allow good adherence of the deposited film onto the substrate. So surface preparation is very important. So typically the chamber looks somewhat like this. Usually it's like you would have seen a bell top jar with a flat bottom, so that you actually can lift the bell and then bring it back. Otherwise it can be simply a fixed chamber. You don't necessarily have to remove the bell or something, so it can be a fixed chamber, and you have evacuation process. So this is how you actually can evacuate and make the inside the chamber extremely low pressure. You can backfill with neutral gas, for example argon, or you can also feed in oxygen or nitrogen if you want certain reaction to take place. But this is not very regular or usual, but feeding argon is fairly regular, because once you evacuate, then when you feed in argon, argon remains neutral, and then also creates a situation whereby undue oxidation is avoided. So this is the substrate, the component that you want to coat, or maybe this is the stage, and on the stage you can place multiple components, like here 1, 2, 3, 4, 5 components. And now once you actually create this high vacuum and apply high amount of current, so now you evaporate these materials, and with the evaporation you actually create a certain amount of vapor atmosphere of the component that you want to coat. So as you so this is, let's say this is the component or the solid that you want to coat, and as you evaporate, so this whole region gets completely filled with this vapor of the material, and this vapor atmosphere now covers the entire range of components that you want to coat. So when you evaporate thermally, say from these regions, you actually can also create, by way of applying certain amount of potential inside, you can create a plasma, and that plasma actually can make the deposition process more efficient. So for example, if you have a heating process which can be either resistance heating or through an external electron beam, and you have your material to be coated, kept in a tungsten boat or some other holding material which can withstand very high temperature, and so you can have a separate heating arrangement, either by feeding current through this tungsten boat, or you can allow the external electron beam to irradiate this place, and then you create this atomic flux, and this is where you keep all your components. For example, in this case, this could be silicon wafer, where you want to, for example, coat certain areas onto the surface, but not all. The areas where you don't want to coat, you cover them up with a certain mask and then expose the rest of the parts which gets coated with the desired metal or the material. So you have multiple advantages. This is a very versatile process, and the deposit, you can deposit almost any material which goes to the vapor state. Very little chance of chemical reaction. In fact, you can avoid completely chemical reaction in flight or in deposit, and very little damage to the substrate, because the substrate is at room temperature or near to room temperature. The chamber inside gets heated up a little bit, but not very high. So when we evaporate from any of these evaporators, and when we want to coat these components, we actually can immerse them. So this is a line of sight, but at the same time, this makes a very uniform coating because it's kind of immersed in the vapor atmosphere. Now, there are also demerits. For example, this is a line of sight process, so you actually can cover only the surface that you are seeing, the vapor is seeing directly. So there could be a process of shadowing. See, for example, if you have a component here and another component here, and if the vapor is arriving this way, a portion here may get shadowed. So we have to make sure that the vapor arrives uniformly from the top or from one of the sides so that it can cover the entire area. In fact, the area of the vapor actually should be wider than the components that we are coating. Then we can make sure that the component is very widely, very uniformly covered. So, so we have to avoid this shadowing effect, possible shadowing effect. There could be non-uniformity of the thickness. See, for example, if you are coating a wide area like this, and if you have only a single evaporator here, you expect that the evaporation should actually cover the entire area like this uniformly, but the rate at which the species will arrive here will not be the same when this region is fairly wide apart. So the coating thickness may vary from the center to the periphery. This is also difficult. For example, if you are thinking of coating tungsten itself, then it's difficult because the melting temperature and the vaporization temperature is high. So you would rather choose materials which are easy to evaporate, which has high vapor pressure and relatively low boiling temperatures. So you can have, instead of enclosing in a chamber like that, you can also create a tube furnace like configuration where you can keep the holders cool by flowing water through these gaps. You can use these openings to pump out the gas inside, evacuate it, and this is the source material, and now you can heat it in a tube furnace. So instead of directed heating, instead of creating in the previous case, if you see, we actually had a boat here, and this boat usually is a tungsten boat which can be heated to very high temperature. So tungsten has the capacity of going up to very high melting temperature, and in the process it has fairly high resistance increases with temperature. So because of this kind of resistance heating, whatever powder you keep here, they get evaporated. So that's how we do, and we expect the evaporated species to go all over. In fact, if we have evaporators surrounding the chamber, then of course we can create a fairly uniform plasma inside, or fairly uniform vaporized atoms inside. On the other hand, we can make a relatively simpler process where we can take a source material and simply place it inside a tube furnace, and with enclosures, airtight enclosures, so we can evacuate, make it very low pressure, and then we heat up the tube furnace so that material from here gets evaporated, and this is the colder portion of the furnace. So maybe the heating zone is confined only here, so that the material is heated and vaporized only in this region, and the vapor, obviously because of the temperature gradient, will move towards the colder region and get deposited onto the substrate that you want to coat. So that's also a possibility. So the temperature that we can heat up to inside the furnace is not very high, maybe up to about 500 degrees centigrade. But no, actually this is micrometer. So this can be fairly thin coating. So the deposit that we create should be thin and adherent. So, and we want to improve the hardness, the wear resistance, the oxidation resistance. And typical applications could be in industries like aerospace, automotive, surgical or medical, in manufacturing using dies and molds and cutting tools, in various kinds of optical devices. Wherever we have use of thin films, even on glasses for tinting, for anti-reflection, for coatings, photovoltaic layer, and so on, for food packaging. In various places, we have these application of PVD. In rare cases, PVD can also take the help of certain reactive gases like nitrogen or hydrocarbon and then create a reaction layer onto the substrate. So the kinetics of the process will depend upon the configuration that we use. So for example, we can use a point source or we can use a small planar surface source. So here the area is wider, so we actually are able to cover wider area. Here the area or the spot that we cover is fairly small. So either a point source or a small planar source. So in case of a point source, the flux will be inversely proportional to the radial distance. So this radial distance. The same thing is true for a wider surface area. The velocity in that case will be inversely proportional to the square of the radial distance. But in addition, it will also depend, here it primarily depends upon this theta k. Here it depends both theta k as well as the theta I, because of the points obviously cannot cover wider area, but planar, if the source is not a point but the source is of certain surface area, then obviously it can cover a wider area, and that is seen here. The overall evaporation rate, of course, will depend upon the mass and the temperature of the material. Actually, you can create special conditions of maintaining a specific temperature and mixture of argon and oxygen to create certain oxide layer. So you actually heat up tin and introduce very low amount of oxygen and allow certain reaction to take place, and this reaction can lead to formation of very thin tin oxide layer. And this tin oxide layer, the beauty of it is that actually by controlling the process parameters, you can change the aspect ratio very significantly. So you can make such very thin wires and rods, and in fact you can have a completely very thin wire mesh in the form of a wool. These kind of large aspect ratios where the diameter is only a few tenths of a nanometer, but the length can be easily a micrometer or close to a micrometer, that can have very high applicability for sensing certain gases, because the specific surface area of these kind of shapes is extremely high. So normal tin oxide film will have one level of sensitivity, whereas if you can create such high aspect ratio, the sensitivity would be much greater. And to create such exotic structures, you actually can modify the conventional PVD and change the process parameters and allow feed in a particular rate and way, so that you can produce such very thin layers with large aspect ratio structures. In fact, you can by way of reaction based PVD, you can create, for example, here you have a nitrided steel, and on top of that, this is where in A you have created titanium nitride, in B you have created titanium carbonitride, and in C you have created titanium aluminum nitride. So you have created a single nitride, you can create a carbonitride, you can create a combined nitride, a mixed nitride. And this is possible not just, it can be done in the same chamber. You simply have to move from one spot of heating to another. So if you are heating by E-beam, you can switch the beam focus from one target to another and then evaporate a different material. So in this process, say for example, you are seeing here that you can have, this is the hard metal that you have. So this is the metal, base metal that you have, and on that you have the titanium adhesion layer. So layer 2 is titanium, and then you have titanium nitride coating. So this is the layer which is titanium nitride, and the titanium nitride on the top surface will also show some micro droplets. Now, why does micro droplets form? Because of typically because of the Gibbs-Thompson effect, that you actually form very small deposits, which because of large surface area actually gets its melting temperature reduced, and as a result during deposition they tend to coagulate. Because of surface tension forces, they tend to coagulate and form a droplet. So this is not desirable. So one has to make sure that such non-uniformity is avoided. We can also create a multi-layer titanium aluminum nitride. Say for example, in this coating, what you are seeing is that this is the base substrate. As usual, like we said, here the base substrate is again some kind of a metal, and on top of that we have our titanium adhesion layer, which is this layer. Then we have titanium nitride layer, and this is the next layer. Then we can have multi-layers. So we can have multi-layers of titanium aluminum nitride or aluminum nitride and so on. The point I am trying to make is that you actually in the same chamber, without breaking the vacuum, without moving, without needing the sample to be taken out, you can make multiple coatings. Now, in all these cases, there is one point which I haven't mentioned but would now like to stress upon, is the fact that whenever you are creating these kind of vapor deposited coating, maybe they are very thin film, yet the substrate coating interface is very sharp. In other words, if this is the substance or substrate that we want to coat, and this is the film that we have created, if you go across at the coating substrate interface, you see if this is the composition, whatever you are saying, and this is the distance. So the coating will have one composition and the substrate will have another, and the interface is fairly sharp. Now because of this sharp interface, you cannot afford to make this thickness of the coating very large, because in that case you build up very high amount of stress at the coating substrate interface, and which can lead to decohesion during use. On the other hand, if you want a very exotic coating like titanium nitride or titanium aluminum nitride on top of an nitrided steel or some other cutting tool, you don't need very high thickness coating. You would rather not have very thick coating, because of the reason that the mismatch will be substantial, and this can actually lead to complete decohesion. But this is the only way you can have such exotic coating created on top of a substrate. Otherwise, you cannot think of a single manufacturing or synthesis process by which you can have a steel, then you nitride, and then you have other kinds of nitrides like titanium nitride or titanium carbonitrides or titanium aluminum nitride, these kind of combinations. So in order to have such combinations, and the beauty of this process is that you actually can have a multi-layer, meaning I can have an alternate layer of, so this is 1, this is 2, this is 3, and I can repeat this a number of times. So I can have such multi-layer coating, and in the process I can make sure that the coefficient of thermal expansion mismatch is minimized or marginalized, and that would depend upon the relative thickness and the relative composition, and obviously the lattice parameter and other important physical properties. So to have a very thick layer directly on top is very difficult, but if I can have such multi-layers, then the adherence is improved, and such a thin film coating actually will perform better under any kinds of aggressive conditions. So time to recapitulate. So what all we have discussed, we said we first have started discussing about thin film coating, and is one of the most versatile method would be physical vapor deposition, where the process involves evaporation of very high vapor pressure material into the vapor state and then allow them to deposit on any colder substrate. That cold substrate, in fact, if it is if the vapor is allowed to go to the chamber surface, there also it gets deposited. But we don't want that. So we create a certain trajectory so that the component is placed on the path of the vapor, where the vapor tends to move, and at that part it could be a metal, it could be a silicon semiconducting material which gets coated. So there's no change in composition. This is where we are different than the previous methods that we have discussed. So we exactly deposit what we have in the form of the target. So PVD can be very useful technique for semiconductor industry, for tooling industry, for precision measurement industry, metrological instruments industry, where we want exactly 2.5 micrometer or maybe 210 nanometer and not 220 nanometer. So it can be very precise. If we have heating, we do need to evaporate, but that's a separate one. But if you also heat the substrate during deposition, then the interface that I was just talking about a few minutes ago, which is usually very sharp, may not be that sharp anymore. So there could be some amount of diffusion, and in the process there could be better bonding. So separate heating during the PVD process can be helpful. We actually can make sure that we are able to coat uniform by having multiple targets or having a vapor zone much wider than the component that we want to get coated. We also can make sure that the coating is more uniform by creating a plasma inside, by introducing certain amount of argon. If we want to create a thicker coating, then we must be aware that this could lead to decohesion because of the stresses generated at the interface. So we can coat pure metal, we can coat compounds, we can coat alloys. In fact, we can make a non-stoichiometric alloy and rapidly solidify, or simply blend different types of powders, crush them, mill them, and then sinter them together, create a target and use that target. The target probably should in that case be able to achieve a right composition, and then use that target as our target for deposition. So we are able to then deposit a very new and a very exotic and a non-stoichiometric composition onto the component that we want to coat. We can make multi-layer coatings, as I was saying, that we can make A, B, C or A, B, or we can vary the thickness of A, B, C sequentially, all by controlling the process parameters of PVD. And we actually can make a modified PVD technique, whereby we introduce certain gases, allow them to react, and then form a coating, thin film, which is not pure, say, tin, but tin oxide, or zinc, not zinc, but zinc oxide. And in the process, we actually can create certain devices or certain sensors or other kind of applications with a microstructure, which is very exotic and not possible by conventional techniques. So we stop here now, and then in the next lecture we'll discuss a special technique of PVD called sputtering. Thank you very much.